This lecture is about examples of the time solutions for some linear systems in state space. We will also try and see a general solution to the linear differential equations and linear dynamical systems. So these examples we'll use to illustrate that there is no difference between the time solutions of systems expressed in state space and whose solution is expressed as an explicit function of time with the solutions that we already know how to obtain via the inverse Laplace transform. The general solution to linear differential equations and linear dynamical systems will allow us to get an idea about how complicated the solutions to these dynamical systems can be in general. So let us begin with some small examples. The system that I'm going to look at is the following system. Let me switch to black. d dt of x is equal to 0, 1, minus 1, 0 times x plus 0, 1 times u, and y is equal to 1, 0 times x. This is the typical system that we already know about, which is made of a mass attached to a spring, where, for example, the mass is 1, the spring has stiffness k is equal to 1, there is no damper, and there is a force u that pushes on the mass this way. The coordinate x is going along this way, and the state, let me call the coordinate y here, and the state x is equal to y dot. The solution to the linear dynamical system reads as follows. X of t is equal to e to the 0, 1, minus 1, 0 times t times x 0 plus integral from 0 to t of e to the minus 0, 1, minus 1, 0 times t times 0, 1 times u d tau. Okay, so this is a tau, sorry, this is not a t. And y is still equal to 1, 0 times x. So our goal here is to compute everything here explicitly for this system, and then we'll specialize things to specific values of u. The first step is to compute e to that matrix times t, which is e to the at, right? It is the same thing as this general formula that I derived before, specialized to this particular matrix. And I obtain the following. So again, we need to compute e to the 0, 1, minus 1, 0 times t. And for that, I use the formula I plus at plus a squared t over 2, a squared t squared over 2 factorial plus etc, etc, etc. So because of this, I get that at, or let's skip, just compute the powers of a for now. Okay, so we have the first a is minus 1, 0. Okay, 0, 1, minus 1, 0. The second one is that squared up. Okay, so a squared will be equal to minus 1, 0, 0, minus 1. Because it is this times this plus 1 times this for the upper left corner, and this times this plus that times this for the lower right corner, and the others are 0. If I compute a cube, I obtain minus a, because a cube is equal to a times a squared, but a squared is minus times an entity, and therefore this becomes minus a, which is 0, 1, minus 1, 0, with the appropriate sign flips. Good. Now we can compute this sum, and we will obtain the following. E to the 0, 1, minus 1, 0 times t will be a matrix, which is a 2 by 2 matrix, with fairly large entries that I'm going to detail now. So the identity contributes a 1 here. At contributes nothing because a is this, okay, and there is nothing in the upper left corner. But a squared contributes a t squared, so it will be minus t squared over 2, okay. A cube contributes nothing, but however, a fourth, you will see, contributes something, okay. So it will be plus t fourth over 4 factorial plus etc, etc, etc. It will be an alternating series made of even powers of t. Let's look at the upper right corner. The upper right corner gets nothing from the identity, but gets something from at. Okay, it gets a t. Then the a squared contributes nothing, but a cube contributes minus t cube over 3 factorial plus etc, etc, etc. And likewise here, we will get the opposite sign, but otherwise the same quantity, minus t plus t cubed over 3 factorial minus t fifth over 5 factorial, etc., etc. In the lower right corner, you will get the same expression as here, which is it would be 1 minus t squared over 2 factorial plus t fourth over 4 factorial plus etc. Now, this is the Taylor expansion for cosine of t. And that is the Taylor expansion for sine of t. Which means that e, the exponential of 0, 1, minus 1, 0 times t ends up being simply cosine t, sine t, minus sine t, cosine t. As a result, we can now compute the solution to our dynamical system explicitly, erasing everything. We write that the solution, the most general solution we can find, which is x of t, is equal to e to the at, so it will be cosine t, sine t, minus sine t, cosine t, times, so that's the e to the at, times x0 plus integral from 0 to t of e to the eta minus eta, sorry. So it will be cosine tau minus sine tau, sine tau, and then cosine tau times b, which is 0, 1, times u. So it is possible to simplify this expression a little bit and say that this is also equal to cosine t, sine t, minus sine t, cosine t, times x0 plus integral from 0 to t of, well, this term is a 0 dot, so we can write it as a column vector only, which will be minus sine tau, cosine tau, times u of tau d tau. Okay, this is what this means. Okay, so and of course there was here I should have really written u of tau d tau. Okay, so with that in mind, there is not much more we can do in terms of having a general and explicit solution to the value of x of t at any time. In order to get something more specific, we need to make x0 specifically take some specific values and u take some specific values. what we're going to do is we're going to do, for example, the impulse response. Oh, before I do this, of course, once I have this, I can write what y of t is, and that will simplify things a little bit. Indeed, y of t is equal to 1, 0 times x of t, and therefore it will be equal to cosine t sine t times x0. So x0 returns a vector. I don't need to put it within brackets. And plus, and we can write just plus, so the same thing, cosine t sine t times integral from 0 to t of minus sine tau cosine tau u of tau d tau. So I can simplify this even a little bit further by putting this inside the integral. And what I obtain is, this is cosine t sine t times x0 plus integral from 0 to t of minus cosine t sine tau plus sine t cosine tau u of tau d tau. Now I can even simplify this a little bit further if I realize that this expression here is also the sine of t minus tau. And I obtain that y of t is equal to cosine t sine t times x0 plus integral from 0 to t of sine of t minus tau u of tau d tau, which is the simplest expression we can get before going into specific cases. Now, back to the impulse response. Let me clear out this area a little bit. And for the impulse response, we assume that x0 is 0 and that u of t is delta of t. Okay, we're going to say that then y of t is equal to literally integral from 0 to t of sine of t minus tau delta of tau d tau. Now, to be more precise, we should say this is, here we assume that that 0 is to the left of this delta, so we can replace this 0 by a minus epsilon here, and epsilon goes to 0 in such a way that we actually properly frame this guy and say that this is also equal to sine of t, because what the effect of impulse is on an integral like this is to take the value of the function where tau is 0. So we get immediately that the impulse response of our system is y of t is equal to sine of t. Now, if you go back to the initial system we had at hand, it was a mass spring system. And we could write that the equations of motion were really x double dot is equal to minus x plus u with some initial condition. If we write that x of 0 is equal to 0, x dot of 0 is equal to 0, and we go in the Laplace domain, we obtain that x hat over u hat must be equal to 1 over s squared plus 1. That is straightforward from here, and we know that the inverse Laplace of 1 over s squared plus 1, which is the impulse response of the system, is indeed sine of t. Therefore, we have complete equivalence between the formula we have gotten here by means of state space manipulations and the explicit formula that writes the solution to the state space system as a function of time, and what we already knew using the inverse Laplace transform. We can go further and compare these solutions if, for example, we look at a step function instead. A step function is the following. Let me first clean up this area. And we just keep everything else. So if we compare and we do a step function instead, then we can write that in the time domain, we apply this formula to a step, which is that, and of course we assume x0 to be 0, in which case we get that y of t is equal to integral from 0 to t of sine of t minus tau, and then u of tau d tau, it will be 1 d tau. Okay, by definition, because u is a step. So when we do this integral, it is very easy to compute, and we get that this is the primitive of sine of t minus tau will be cosine of t minus tau between tau is equal to 0 and tau is equal to 1. Is equal to t, my mistake. Okay, yes, the reason is because d dt of course d d tau, let me do it again, d d tau of cosine of t minus tau is equal to precisely minus sine of t minus tau times d dt of minus tau, which is minus 1. Therefore, these two minuses go away, and that's what we get. Now, this is equal to the value at t is cosine of 0, which is 1, and then the value of the of the cosine at tau is equal to 0 would be cosine t. Okay, so that's what the step response of our system looks like. And indeed, when t is equal to 0, this thing is equal to 0, and so the system slowly starts and does the following. Okay, it starts and does something like this. That's the nature of the oscillation that we see as far as y is concerned as a function of time. Now let's see how that matches with the what we already know, okay, which is the Laplace approach of everything. Laplace will tell us that the step response, so the step response for the system will be the inverse Laplace of 1 over s times 1 over s squared plus 1. Indeed, the step response in the Laplace domain is 1 over s, and the system is 1 over s plus 1. We already know that transfer function. To do that, I remind you that it is easier to just compute things by yourself and say, I'm going to do a partial fraction expansion of this guy, which I will write a over s plus bs plus c over s squared plus 1. I reduce that to the same denominator, and I know that this must be as squared plus 1 plus bs squared plus cs divided by s times s squared plus 1. Now that means that a plus b must be equal to 0 because we don't have any powers of s squared here. We then get that c must be equal also, let's see, hold on a second. We get that c must also be equal to 0, indeed, because there is no s term. And finally, we get that a must be equal to 1, because a times 1 corresponds to this 1. And therefore, what we end up is saying that this is very much like, I replace a by 1, b by minus 1, and c by 0. Now, the inverse Laplace transform of this is what we need to compute. And the inverse Laplace transform of 1 over s is simply 1. And the inverse Laplace transform of minus s divided by s squared plus 1, check your formulas, is precisely minus cosine t. So again, what we have is the exact same solution between what we knew how to do before, which was the Laplace transform or the inverse Laplace transform exercise, and the computation directly in the state space and always in the time domain. Another thing that we can try is see what happens if you have some initial conditions. Let me clear out this area and try and see if the system behaves the same way when we derive the pure time domain response of the system than if we use the Laplace transform business. So for that, I must remind you that if our system is this mass attached via a spring to a wall, and there is a u here, okay, we have that the differential equation is x double dot equals minus x plus u if there is some initial condition x of 0, okay, which will be equal to y and then y dot of 0, which we will also rewrite as y0, y dot 0. Then I can use the Laplace transform to get the solution to this guy. Okay, I will assume for simplicity that u is equal to 0. I can always use the superposition principle to superimpose the effect of u, which we already know, to the effect of the y's, and we obtain that the Laplace transform of x double dot will be, as we know, s times x dot, or x times the Laplace transform of x dot minus x dot of 0. And that is equal to s times the Laplace transform of, s times the Laplace transform of x minus x of 0 minus x dot of 0. Okay, so I garbled things here a little bit. Forget about that x. Okay, the way I have written things here, this is not y of 0, it is x0 and x dot 0. Okay, my notation says here that x is the position, not to be confounded with here where it is seen as the state of the system. If you want, we can just use y as the proper notation and replace this differential equation by y double dot is equal to minus y plus u. At least this raises the ambiguity about whether we have what we're working with. Okay, y is the position here of the mass. All right, so using that generic formula, we obtain that s squared y hat minus s y0 minus y dot 0 must be equal to minus y hat plus u. We assume u is 0, and we get that y hat times s squared plus 1 must be equal to s times y0 plus y dot 0, and another way of saying it is that y hat is equal to sy0 plus y dot 0 divided by s squared plus 1. Okay, so that's my y hat. Okay. Now, what we can do is use the inverse Laplace transform to clean that up. Okay, so I'm gonna circle out everything I don't need. And I get that the inverse Laplace transform of this is y of t would be s over s squared plus 1. That is cosine of t times y0, and then 1 over s squared plus 1 will be plus sine of t times y dot 0. Okay? Now compare that with this, and what we obtain is precisely, given that x0 is y0, y dot 0, what you obtain is precisely the same formula, because here you get y of t is equal to cosine t sine t times y0, y dot 0. Okay, that's what this guy gives us, which is precisely cosine t y0 plus sine t y dot 0. So there is a complete agreement